And P is the midpoint of arc BC. So we could just use the N center X center lemma. Should be easy enough. Yeah, these were a lot harder than I thought. So this should be P and that should be I. And then we draw the reflection of P over BC. And then we have the orthocenter of BIC. And it's way up there. Let's see if I can bring it down a little bit. There we go. So that's point H. Let's close this. And we just want to show AH, IP prime, and BC concur. So HI, so hold on a sec. Whoops. So maybe it's worth drawing the inner circle. So I is the orthocenter of BHC. And HI and that point are collinear. I'm going to show AH, IP prime, and BC concur. What if we reflect all three of those across? So let's do this. I'm going to draw the circumcircle BHC. And if we reflect H over BC, and then we reflect I over BC. So if we reflect I over BC, it's going to lie on the circle. Right? If we reflect H over BC, so if we reflect P prime over BC, we just get P. So basically, we want to show AH passes through that. Yeah, we're just using symmetry, right? We just need to show AH and E are collinear. And is PI tangent? No, PI is not necessarily tangent, or PI prime. Okay. Yeah, the midpoint of BC. I mean, maybe it's AF intersect IB. Okay. How do you solve it? Project P prime F infinity onto BC. Okay. And what do you project through? From I. Okay. And from A. Okay. So P goes to this point. P prime. Sorry. Okay. P prime. Okay. So we have J, E, F, D is harmonic. And then if you have H, I, G, B, so since HIGB is E, then we need to have, okay. Okay, so basically, yeah. All right, so let me write this all out. So once we know those cross ratios are both 1, okay, then we're just projecting through that point. Okay. So it's H, I, G, D. Okay, so sorry, help me out here a little bit. So once we know that HIGD is 1 okay, so we have HIGD and we have then we have EJ DF. So we have EJDF is HGID. And how does that HIGD? Okay, so I mean, so basically that's the same as saying EJ dF, and if you project from I, okay, then you would also get EJ dF. So since they have the same cross ratio, then okay, so they both have to align at, okay, so we don't even really need I prime. Okay. Sorry. So I'm going to hide this stuff. Now we don't need this, I don't think. Okay. Okay, so here's what I'll do. I'll say let P prime I meet BC at E prime. And let AH meet BC at E double prime. And then projecting through A onto BC. Then we have HIGD is equal to EJFD. And projecting through I onto BC. We have P prime P F, and then that. I'll just say we have -1 is equal to that, which is equal to, this should be E double, oh, sorry, I forgot all my primes. So E prime JFD. So this should have 2 primes. This should have 1 prime. Is that right? E prime JFD. And okay. And then you're saying by the Iran lemma, this first one is -1 because, so HIGD is -1 by the Iran lemma. Why? Let me just think about that for a second. G lies on the polar of A by a well-known lemma. Okay, I'll just say that. And then I'll move on to the next one. Let F be the midpoint of BC. G equals AF IH lies on the polar A. Okay. Oh, okay. Oh, yeah. Okay. Bye. Yeah, that helped me a lot. Sorry. Oops. And from there, that implies HIGD equals -1, which implies E double prime equals E prime equals E. And that implies AH IP prime and BC concur. All right, looks good. So that was a quick one. Let's see what else we have. This one looks like a quick one. So, sorry, I just feel like doing easier ones for now, but maybe we could go back to that other one in the beginning after this, if we solve it quickly. So I is the end circle. Yeah, this one's probably easy. Let's see how quick we can do it. This is D. So then we reflect M over AI. Oh, did I do this on my channel before? I mean, it looks like it might use the IM lemma. So we reflect M over AI, and that's K. And we want to show DK is perpendicular to OI, and they didn't define O, but I'm guessing it has to just be the circumcenter of ABC. So, okay. You guys probably already solved it by now. Let's see. Maybe. This is O. So we reflect M over AI. Maybe it's worth drawing this point down here. Whoops. We know MI bisects AD. And I think, did I prove on my channel that AK, okay, no, AK is not perpendicular to BC. Let's draw this point. So yeah, this is an interesting, looks like a spiral similarity or something. I don't know if this will help, but might as well use this fact. MI and H are collinear. So I guess one way we could do it is we could try to show the power of D. So the power of D with respect to both circles minus the power of K with respect to both circles is, we want to show DI squared minus DO squared is KI squared minus KO squared, right? So we could probably do something with the powers of the points, right? H is the midpoint of AB. But I think, so we want to show that if you take the DI squared minus DO squared equals KI squared minus KO squared, but that's the same as showing the difference between the powers of D with respect to both circles is the difference between the power of K with respect to both circles. So the power of D with respect to both, that's just dB times dC. And the power of K with respect to both, I don't know if there's an easier way to do that. Well, by symmetry, the power of K with respect to the end circle is the same as the power of M with respect to the end circle, right? So that would just be MD squared. Now, what's the power of K with respect to the circumcircle? I think that's the hard part. Although maybe it's not as hard as I think, because if we draw this, so Fk is equal to Fm, and then maybe we could find this. So does Kd or Kj equal something special? I don't know. So we can find Fk. Can we find Fj? Is it just, if we label this point, then wonder, so FL times Fj is Fb squared, is Fi squared. And I wonder, I don't think FL equals FO, does it? Seems unlikely. Yeah, it's not true. But triangle FJG, so FG is a diameter, right? So and in fact, AJ is equal to AG, right? Basically, I want to find the power of K with respect to the big circle. That's my whole goal here. And we know KF is MF, and KL, that's what I'm trying to find. Maybe there's an easier way to prove this. Like maybe we could use orthocenters. So maybe D is the orthocenter of some triangle with O and I. Maybe D is the orthocenter of OKI. No, I don't. No, it's not. Are D, K, and G collinear? No. Yeah. Okay, so we'll call that Q. Let me delete, yeah, this. And then Q is the orthocenter of the contact triangle. Is there any circle through F and J that's significant? FJ. So basically DQ is parallel to AF, right? Let me try this again. So I reflect J over AI. I get that point. Is there anything special about that point? Is K, wait, okay, so by symmetry, these all concur, right? So maybe that helps. Oh, is that, no, that's not true. I doubt that K is the midpoint of, yeah. Okay. So yeah, is there anything special about J prime? No, does CJ prime equal CF? That would surprise me. Oh, that's not true. Yeah. Um, hmm. I would be very surprised if Fj equals Fn, but I'm going to check it. Yeah. So actually, the problem is equivalent to saying that B and K are the same distance from the radical axis of these two circles. But I don't know how helpful that is. But you know what we could do? There is a way to calculate, actually, there is a way to calculate the power of K if we use Casey's theorem. So let's draw this circle. So the difference between the power of K with respect to these two circles, it's twice OF times the distance from K to BC. Oh, we didn't even draw this, but this is cyclic right here. I wonder if that helps. Okay, so I think I've kind of reduced the problem to a calculation here. But it's a little bit of a complicated calculation, but let's try it out. So We have let's see how this works. We have the power of D with respect to O minus the power of D with respect to the in circle. So I'll do it like this. That's equal to AD times DC minus 0, which is AD times DC. Okay. And then the power, we want the power of K with respect to I minus the power of K with respect to O. So by KC, so first I'm going to say the power of K with respect to I is equal to the power of M with respect to I, which is equal to MB squared. That's by symmetry. Oh yeah, you're right, BD times DC. And then for O, we have by Casey's theorem, we have the power of K with respect to O minus the power of K with respect to F. So here's where I'm going to use circle F. That's twice the distance between the centers. So that's twice OF, which is the radius, times the distance from K to BC. Okay. And the power of K with respect to F is KF squared minus KF squared minus BF squared. So is equal to, so that's KF squared minus BF squared, which is MF squared minus BF squared. And so what's the distance? That's net minus BM squared. Yeah, so that would be, yeah, negative BM squared. Or actually, yeah, I'm a little confused with the signs. Is the power negative if it's inside the circle? Yeah, I think it is, right? Okay. So, all right. So we want to show that if we take this plus this, that would give this plus this minus this. Yeah, I think that's right. So then we have BM squared and MB squared, and OF is the radius of the circle. So okay. All right. So how do we get, so the distance from K to BC, it's going to be twice the distance from E to BC. Yeah, I don't know if that's that easy to get.
I think everything is easy except the power of k, but we have calculated it.
So how do we get the distance from K to BC?
I don't think we need that if we have the power of k. Oh, that is it with respect to f. Oh.
Oh yeah, this is the power of K with respect to F. Yeah, and then the distance from K to BC. Yeah, I just don't, yeah, this might be a little tricky here. So I guess we could drop a perpendicular from E to MF and try to find that distance. So ME squared is that distance times MF. And so it would be twice whatever that distance is. So that's one way to do it. But then ME squared, could we find that somehow? So we know MEF is similar to FAG, right? So basically, yeah, I think it's all just similar triangles kind of, because basically the distance from K to BC, it's 2RM. And triangle ERM is similar to triangle EMF, which is similar to triangle GAF. So we have basically MR times MF is ME squared. And ME and MF are similar to GA and GF. So yeah, I don't know if this all reduces to a calculation. And GF is twice OF, right? So this we could just say is like GF times the distance from KB to BC. Yeah, let's write this out. This might just all be a calculation. So I'll write it like this. So that should be GF times 2RM. And then we have RM times MF is ME squared. So that means RM is ME squared over MF. And then we could probably write that in terms of AG and GF, right? So I'll just say it like this. And then this should be equal to AG squared over GF. But then we need to take out a factor. AG squared over GF. But if we do that, we're scaling everything. So then we need to multiply it by, basically we need to divide out the ratio. So times GF over, or times MF over GF. Over GF. Is that right? Yeah, I think that's right. And then MF, but MF times MG, FM times FG is equal to BF squared. Yeah, what is tricky. So wait, so if we multiply this out, so it would be GF times twice that. So I'll go swap these. And this should be AG squared times 2MF over GF. All right. And then we want to show if we take this, and if we add this, then we want to show, and then we subtract this. So BM squared minus MD squared. Then we want to show we get this. Maybe that's not so easy. But this we could say is D, instead we could say it's DO squared minus the radius squared. And yeah, it might be bashable, but I think it might be a little difficult. So yeah. So AG over GF. See, the problem is we want to like, Yeah, I guess I don't really know what we do with AG. So yeah, this idea might be a little harder than I thought. But BM squared is MF times MG. Yeah, this would take a while, I think. Yeah, so maybe there's a faster way. Let's see. What if we reflected D? So we could try this. We could try reflecting D over AF, and that should lie on the in circle. And we could reflect O over AF. Basically reflect the whole figure over AF. And then we want to show, so instead of BK is perpendicular to OI, it would be D prime M is perpendicular to O prime I. And I wonder, sorry. Because O prime bisects AF. All right, so we have Khan joining us. All right, thanks for joining us. So yeah, we have about 20 minutes left. And we're on our third, I think it's our third problem, maybe our fourth. It's all right. Yeah, thanks for joining still. So yeah, the initial problem is kind of a simple statement.
I think I'm very close to solving the first problem.
Oh, really?
Yeah, I found some new things and proved some.
All right.
So maybe we can finish it then.
All right.
So you have to draw in some new points. Intersect, take the line IH.
Okay.
And intersect it with the two small in circles.
Okay. So we have this one and this one.
Okay, then I proved that AVF is collinear.
A, B, and F. Okay.
Yeah.
Let me draw that.
And also draw that line, don't just segment.
Okay. And it looks like it passed through T also, right?
I'm not sure if it passes through T, but it concurs on BD, and I have proved that.
Okay. Let me, yeah, okay, you're right. Yeah, it doesn't concur at T, but it concurs at some point on BD.
Yeah.
Okay.
Also, I proved that Okay, so we'll need to take another intersection, I think. No, just a second. I proved also that AKJ are collinear.
Okay, A, K, and J. All right.
And by symmetry, C, K, and F.
Okay.
And also then E, G, K, W is harmonic.
Okay. Wow, there's so much stuff here.
Yeah.
Okay. Okay. Let's see. So
Also, another thing I should say is that W, that is like the touch point of the X circle by the
okay.
both the triangles. I mean, U is the CU is like a well-known line, and
Yeah, just because this is the topmost point.
yeah,
Yeah.
like
Okay, so yeah,
homosexual.
it's kind of obvious then
That
that these would concur.
yeah, and also it is easy actually to prove that CU and J are collinear. That is also a homotopy since OJ and HU are parallel. Then you just need to prove that OJ over HU, which are the radii of those two circles, is OC over HC. But that is obvious when you take the touch points of those two circles with BC.
Yeah. So I mean, because basically, like, what was it that were you just trying to show A, V, and F were collinear?
Yeah, I switched to J, U, and C. Sorry.
J, U, and C. But yeah, that's kind of obvious because if you look at in this kind of direction that these parallel lines are going, like F and V are the topmost points of those circles, right? So by homotopy, it has to take V to F, right?
It is a homotopy indeed.
Yeah.
And because of AVF collinear, and that we can prove that A, K, and J are collinear. I think since KV is actually that is also a homotopy since those are the bottommost points.
Yeah, those are the bottommost points.
And since we know that then AJ, CV, and WE concur, then we have a harmonic bundle EG KW.
EGKW. Okay.
So that is like the reasoning of everything I just
said. Interesting. So showing that Fi and E are collinear, that's basically the same. Because let's see, WE, CF, and AU concur. So that means that if it were true that these were, oh, but we'd have to take the intersection of that with, I'm sorry, with AJ. Okay. So let me think about this. So the homothency at A, it takes V to F. That same homothency is going to take I to O, and it's going to take K to J. And I wonder what it does to E. So we could just, basically it takes E to this point. So saying that F, I, and E are collinear is the same as saying that this point O we want to show that Z, O, but it takes V to F. Yeah, it's kind of weird because the homothency, it takes V to F, but then it takes I to O. So it's like flipping them around. Okay, so E, are E, H, and J linear? It looks
We
like
won't prove that.
that E, H, and J are collinear.
That is exactly the problem.
Oh yeah, it's just symmetric, yeah, to I, E, and O. Okay. So in the beginning, we were trying to show that GK over G, or EK over EG was the ratio of the radii. I wonder if everything we found out can help us with that. So you said W, was it W, E, K, and G are harmonic?
Yes.
So maybe that could help us with that, because then GK over GE would be like WK over WE or something. WG over WE, I think. And once we have that, Hmm. All right. So yeah, the EH and J were collinear. Is there any kind of thing that would have to be harmonic? Let's see. If they were, then if we look at triangle LJC, we'd have EJCO. Yeah. I don't think that does much. Yeah, it's interesting that, yeah, I feel like you found a good number of things.
I think we solved it.
Okay.
Okay, so just a second to see what I done. What I've done. Okay, so we would want to project EG KW through I.
Okay.
And onto FJ.
Onto FJ. Okay. So K goes to infinity, G stays at G. So you want to project E and W onto FJ. Okay.
Yeah. E should go to F, but we need to prove that.
Okay.
And then you should draw the IW.
Okay.
And that must be the midpoint. So we need to prove that, basically.
Yeah.
So I think that was obvious, but let me just see.
Because I is the midpoint of VK. So
yeah, and they're parallel.
Okay. So VI equals IK, so FZ equals ZG. And then if we project FZG infinity through I, we get WG E. We want to show it's EK, but we know those are harmonics, so that solves it. Interesting. So wait, did we have to know that I forgot how we showed that these were harmonic. Do we have to know that these concurred on it, like AV and CU?
This solution depends on those things that I have proved.
Concurrent.
So how do we prove that it is harmonic? Well, we have that AJ, CF, and WE concur. And so when you have those which concur, that is like complete quadrilaterals in those harmonic bundles.
Okay. All right. Very interesting. Okay. So did we even need point L for this proof?
I think in the end we didn't need that, and that OE bisects.
Yeah, so I don't think we needed S.
Yeah.
And did we need L?
No, since that was just to prove OE.
Okay. All right, so. Okay, so I'm gonna write out a summary. So I'll just say label the points as shown.
Perfect.
Yeah. A, V, and F are collinear since FG is parallel to VK. So by a homothency, since FG is parallel to VK. And then similarly, C, U, and J are collinear. I'll say they concur at the touch points of the A and C X circles of triangles ABD and CBD, which is a point W lying on BD. That's easy to show. Okay. And which is a single. And then once you know that, since CF, AJ, and WE concur, so AKJ and CKF are also collinear by homothency. All right. And then AU, CF, and WE concur. WE concur, and that means that WKGE is harmonic. And projecting through I, so VI equals IK means that FZ equals ZG. And then we project through I. So we have -1, which is equal to, so FZ is equal to ZG. So FGZ infinity And that should be equal to WK G, and now we're going to want to do IF intersect WD. And this implies that E equals IF intersect WD, which implies that I, E, and F are collinear. This is an awesome solution. Thanks a lot, Stefan. All right, so we are out of time now. So I'm very happy we were able to solve this one. So yeah, thanks everyone for joining and staying this long. And for those of you on YouTube watching, if you want to join us in the future, feel free to email me at mgreenb801@gmail.com. We meet every Sunday at 8 a.m. US Central Time. So my email is in the description of my video. So thanks again for watching and have a great day.